good evening. Welcome back to Physics Wala. So how are you, Irian? Okay, can we begin? So today we are going to discuss about the first chapter of the chemistry, that is solutions chapter. That is a very important chapter for your board exams and it's a big chapter having the more weightage. So we can begin the session, and we already learned about solution in our previous classes, class 11 and class 9, right? So we had an idea about the solution. So what is a solution? Can you do the comment? What is a solution? Okay. So, a solution is made up of two components. Minimum two components is required for making a solution, that is a solute and a solvent. And before that, we should know how we can make a solution, right? So, what is a solution? Please do comment. We all are familiar with solution in our daily life. We are using a lot of solutions for drinking purpose also, like medicines, like many solutions are using in our daily life, right? So what is a solution? How we can make a solution? Can anyone do the comment, please? No one is talking. No one is doing any comment. Why? What happened to you? You were very active yesterday, right? So, solution means, look here. For example, if you are taking a beaker and we are going to add some little of sugar into it. Okay. So, I added some sugar. This is sugar molecules, sugar crystals. To the sugar, I am going to add like 30 ml of water. What will happen to the sugar? The sugar will dissolve in the water, right? The sugar starts to mix in the water and it will form a sugar solution, right? So, it will form a sugar solution. Why I said like sugar solution? What is the reason behind that? Because the sugar dissolved in the water and it formed sugar solution, right? And there are two components in it. Sugar is the one component and water is the other component. And can we make a solution only with one component? If there is only water, just think about only water in this beaker. Only water. Is it a solution? No, right? Why? It's just water. Can we call it as a solution? No. So, for making a solution, minimum two components are required, or more than two components are required to form a solution. So here we are going to learn about the solution made up of only two components, that is a binary solution. What is my binary solution? A solution made up of how many components? Two. Binary means two components. Got it? So when a solution is made up of two components, it is known as binary solution, and a solution is actually a homogeneous mixture. What is it? A solution is a homogeneous mixture. What is it by homogeneous? Homogeneous. Anyone know what is homogeneous? Homogeneous means the composition will be uniform throughout the solution. That means if you are mixing, like the previous one, I am taking salt or sugar in this beaker and it is filled with water, H2O is there, and here I am taking salt. And it is completely dissolved. The salt is completely dissolved in the water and I tasted 1 spoon of that. What is the taste of that liquid? It will be salty taste, right? The second spoon also it will be salty taste. Third spoon also the salty taste. Fourth one also. Till the end of that liquid, it will be only salty taste. Why? Because the salt is completely mixed with the water. That means the composition will be uniform throughout the solution. There won't be any change in the composition. That is the uniform composition. If a solution is having a uniform composition, that kind of solution is known as homogeneous solution. There are two types, heterogeneous, homogeneous is there, but solutions are homogeneous. That means the composition will be uniform throughout. Just think about if you are adding a salt or sugar and water, the taste will be throughout, it will be same. So only salty taste or sugar taste we will be getting, right? So, before that, we should learn about two terms that we learned in our class 9. You remember the terms solute and solvent. For example, here I mixed salt and water, right? The substance which is present in lesser quantity. The substance which is present in lesser or smaller quantity is known as what? Solute. The substance present in lesser quantity is known as solute, and the substance present in greater quantity is known as what? Solvent. So together they will form a solution. Solute and solvent together they will form a solution. So we can make an equation for the solution. What is a solution? Solution is a mixture of, it is the mixed by solute and solvent. So if we mix a solvent and solute, we will get a solution. So minimum two components are required. Without two components, it won't be a solution. So minimum two or more components are required for forming a solution. Hello everyone. Hello, good evening. So it's clear. right? So solution is made up of solute and solvent. Solute means present in what? A lesser quantity, and solvent is present in greater quantity. Together they will form a solution. So they are a homogeneous mixture. Homogeneous means what? The composition will be same throughout the solution. There won't be any change. If you are tasting the liquid, it will be same. Got it? Clear, right? Then, so we can go to the next one. Like there are lot of solutions like solid solution, liquid solution and gaseous solution. You know about solid solution, gaseous solution, liquid solution. From the name itself, we can learn that there are three types like solid solution is there, liquid is there. There are three states of matter that we are familiar, right? Solid, liquid and gas. Solid solution means the solvent will be solid. Liquid solution means solvent will be liquid, and gaseous solution means solvent will be gas. The greater quantity will be in this word. Okay, solid, solvent will be the solid. Liquid solution means solvent will be liquid. More quantity will be liquid. Then gas solution means what? Gas will be the solvent. And the solute can be different. It can be solid, liquid or gas, anything. Got it? Okay, then. So we can go to the table again. There are different types. Like first one is solid. Look here. Solvent is solid. Solute is also solid. And this can be asked for your MCQ question. We are having 16 MCQ for our board exam, and out of this table they are repeatedly asking questions like give an example for solid, and sometimes example will be given and they will ask which is the solvent present here, like that. So if both are solid, and the main example is alloys or stones. What is alloy? Alloy is a mixture of different kinds of metals, right? It can be a mixture of iron, nickel, chromium, and we can mix different types of metals. It will form an alloy. Okay, so first example is alloys and stones. Then next one, solid and liquid. That is very familiar thing that we are using in our daily life, like solid and liquid. Okay, so solid and liquid means salt mixed in water, sugar mixed in water. It is an example for solid and liquid. Next one is solid and gas. Are you familiar with that? That is not familiar one for us, right? We can mix solid and gas. The main example is iodine in air. Iodine is solid thing. Iodine can be mixed in air. Iodine vapors in air. Okay, thank you. Then next one. Then liquid and solid. That is a great example that we are using in many reactions also. Mercury is a liquid metal. That mercury can be mixed with other metals. That means liquid and solid. The next example is liquid. Liquid is the most commonly used example. That means we can mix alcohol and water, right? Both are liquid that will be completely dissolved. And many other juice with water. We can mix like different liquids can be mixed. Both will be liquid. Solute and solvent will be liquid. Then next one is liquid and gas. Moist air. So just look around us during the humid or rainy season, the moist air will be there. In the air, water content will be there. That is liquid and air. Then next one is gas and solid. That means hydrogen on palladium or platinum or nickel. Then gas and liquid. Gas and liquid that we are using to make like carbonated drinks. You are familiar with carbonated drinks, and we are drinking lot of carbonated drinks like 7-Up, Mirinda, Pepsi, right? How it is made? Like the soda waters. How it is made, you know? The water will be pumped with high pressure carbon dioxide. So what happens when we are pumping carbon dioxide at high pressure? The carbon dioxide will be mixed with the water. So gas is the solute, the lesser quantity is carbon dioxide. Water is the bigger quantity, that will be the solvent. So that is meant by gas in liquid. Aerated, like aerated water means carbonated drinks. Okay, clear? Got it? Then next one. Gas, both gas. Just look around. We are around lot of gases, right? It's a like many mixtures like hydrogen is there, oxygen is there, carbon dioxide is there, helium, argon, lot of gases are mixed, right? That is gas. Okay, so these are the examples for different types of solution: gaseous solution, solid solution and liquid solution. Got it? Okay, now we are going to the main part of this chapter, that is expression of concentration of solution. We can express the concentration. What is by concentration? The amount of quantity of the solution by using different concentration terms that we already learned in class 11, like molarity, normality, mole fraction. Like these terms we already learned. Again we are going to learn about these terms, and we are going to apply these equations and problems. Okay, and these are the sure questions for your board exams. We can start from the small, the main concentration term, that is solubility. Actually, it is not in our textbook. Only solubility is there. No need of this equation, but we should know it is solubility. What is solubility? Solubility means the maximum or the specific amount of solute that can be dissolved in a solvent. Okay, so there will be a specific amount. For example, if you are taking a bucket of water, a bucket of water is there, Like for example, 1 liter of water is there. Can we dissolve 50 kilogram of sugar in this 1 liter of water? Is that possible? Can we dissolve? Can we dissolve 50 kilogram of sugar in 1 liter of water? Is that possible? No, it is not possible that 50 kilogram of sugar won't dissolve in this 1 liter of water. And also we can take an example, if you are taking 1 glass of liquid, in that can we add 5 teaspoons of like sugar? It won't dissolve, right? There will be correct amount like maximum 2 spoon, and in this 1 kg will be dissolved completely. So there is a specific amount of solute that can be dissolved in a specific amount of solvent. Furthermore, we cannot dissolve. So there is a correct amount that is known as solubility. So what is solubility? It can be asked for 1 mark. What is solubility? Solubility means the specific amount of solute that can be dissolved in a solvent. Clear? Got it? And for that, we can use one equation S equal to weight of the solute divided by volume in liter. This equation we are not using anywhere, but we should know, like for our competitive exams, we require the solubility equation. Clear? So what is solubility? It is the weight of the solute in grams divided by the volume of solution in liter. Then we can go to the next term, that is concentration in parts per million. Parts per million means that trace quantity. That much lesser quantity we can use this equation to find out the concentration, that is mass of a component. There will be lot of components, right? Component A will be there, B will be there, C will be there. Sometimes many components will be there in the solution. So if we want to find out the concentration of a component, we can give A. Mass of A divided by total mass of the solution into 10 raised to 6. Why we are using 10 raised to 6 here? Because it is parts per million. That much very trace quantity, lesser quantity. Clear? Got it? Okay. And these things, just read the equation. We are only using mainly like mole fraction, molarity will be using, and mass fraction. Got it? So, next one is a main important equation. We can go to the molarity that we are using for our problems. Many problems are coming from the section, that is molarity. Molarity is denoted by the letter capital M, and molarity is used to express the concentration of number of solutes, related to the number of solutes. So, the equation is given by the number of moles of solute present in liter of the solution and is denoted by capital M. We can write the equation. No need to learn this equation. I will give you the equation. Okay. When molarity of a solution is 1, it is called 1 molar solution. That is required for our practical exam. Sometimes the the practical examiner will ask you the question, what is 1 molar solution? What is 1 molar solution? When the molarity of the solution is equal to 1. So we can do the derivation here. Listen. Molarity. Molarity is represented by the letter capital M. Molarity means number of solute, number of moles of solute divided by volume of solution. Okay, it is not solvent, it is volume of solution in liter. Okay, so majority of the question it will be given only in milliliter. We need to convert into liter, then only we will be getting the answer. Okay, so be careful. And the moles also, the equation is not available in textbook because we already learned it our class 11. So we are going to substitute here. Okay. Clear, right? So, what is the equation for molarity? Molarity is given by the equation number of moles of the solute divided by volume of the solution in liter. So, first we want to calculate the number of moles, then we want to convert the milliliter into liter, then substitute in this equation. And we can write the unit as mole. Capital M will be the unit. And before that, what is the equation for number of moles? Number of moles. Number of moles is given by the equation. The given mass in the question, there will be, wait a minute. There will be a given mass in the question divided by its molar mass. Hello, is okay, right? Okay, done. Yes. There is some problem related to the both. That's why I went out. Okay. So where we stopped? Yes, here, molarity. So molarity, the number of moles can be calculated by how? By using the given mass divided by the molar mass. Molar mass, we should know, we should learn the molar masses of oxygen, hydrogen, sodium, potassium, carbon, like the main elements, we should learn the molar mass, then only we can substitute here. So the equation to calculate the molarity is the number of moles of the solute divided by the volume of the solution in liter. Got it? Clear? Okay, then next one, how to find the number of moles given mass divided by the molar mass. Now I am going to give you a problem. Try to solve the problem. Okay, together we can do. The problem is, write it. Calculate the molarity. Calculate the molarity. Calculate the molarity of 5 gram NaOH dissolved in 450 ml. Dissolved in 450 ml of water. So everything is given in this equation. How we will find the molarity here? 5 gram NaOH. So when we get a question, we should write the given things. First, we should know which is the solute and solvent present in this question. Okay, so 5 gram NaOH means this is the solute. Lesser quantity it will be the solute and greater quantity it will be the solvent. No doubt in that, right? Now, okay, clear, right? So we can substitute the equation. We know the equation. First, we should find the number of moles of solute. So number of moles of solute is given by number of moles of solute is equal to given mass. What is the given mass in the question? It's 5 gram. Okay, 5 gram divided by what is the molar mass of NaOH that we don't know, that we should calculate. It is not given in the question also. So the molar mass of NaOH, Na, it is 23, oxygen 16, hydrogen 1, and when we add it, we will get 40. So 5 gram divided by 40 gram per mole. So we will get the answer like 0.125 mole. Everyone got the answer right? Everyone got it right? Clear, right? Okay, done. So we got the number of moles. Now we can go and substitute this main equation of the molarity. That is, molarity is equal to number of moles of solute. Number of moles of solute divided by the volume in liter. Volume in liter. Don't forget to convert into liter because already in our question is given in what? Milliliter. Okay, so we can convert, like number of moles we got 1.25 divided by volume, it is 450 ml. That means it should be converted into 1000. So it will be like divided by 1000. So when we solve this, we will be getting approximately 0.27 something, 28 capital M molarity. So this is a manner to find the molarity. So first convert the milliliter into liter and find the number of moles of the solute. Just substitute. Okay. Clear? Any doubt in this one? Okay. So molarity is over. Next concentration term. Okay. So next concentration term is what? Molarity. Molarity is very important, like molarity. Molarity means not in the volume terms. We are calculating in the terms of mass. Mass of the solvent in kilogram. Only one change is there. Weight of the solute. That means weight of the solute by molar means what? The number of moles of solute divided by weight of the solvent in kilogram. We can rewrite the equation. Okay. So learn it. Molarity is given by the equation small letter m. Small m equal to number of moles of solute. Number of moles of solute divided by mass of solvent. Not solution. Solvent in kg. Solvent in kilogram. Is that okay? Clear? So we got the equation. How we will calculate the molarity. Lity, not ritty, molarity. It is given by the equation number of moles of the solute divided by mass of the solvent in kilogram. If we use this equation, we can find the answer for the molarity. Okay, then next one is mole fraction. Mole fraction is very important. We know that a solution is prepared by how many components will be there? A beaker will be there. For example, if you are mixing alcohol and water, A will be there. B will be there. Two components will be there. So if we want to find the mole fraction of a component B and or mole fraction of component A, how we will find? So mole fraction means solute present in one component divided by total number of moles that we can look. Okay. So if there are two components, for example, A and B together forms a solution. Mole fraction is denoted by the letter. It is very, very important. Okay. Mole fraction is given by the equation chi equal to. For example, we are going to find the mole fraction of only A. We can write chi A given by Na divided by Na plus Nb. Na plus Nb. Got it? So how to find the mole fraction of A? Okay. I will make it slow. Okay. So we can find the mole fraction of A by the equation chi. Chi A equal to what? Na divided by Na plus Nb. What Na and Nb? Na means number of moles of solute A, number of moles of B, that is Na and Nb. Now if you want to find the number of mole fraction of B, the equation only one slight change is there. It will be like Nb divided by Na plus Nb. So what is Na and Nb? Na and Nb means number of moles of B and number of moles of A. Got it? Clear? So, and one more thing is there, if the solution contains n number of components, for example, A is there, B is there, C, like up to n number of components are there, the total sum like chi A plus chi B up to chi n, it will be equal to unity. Clear? The sum of the mole fraction of the individual components, it will be equal to unity. Unity means what? 1. And if there are only two components, like only A and B, if there are only two components A and B, we can write the sum like chi A plus chi B equal to 1. Okay, so this is the equation that we are going to substitute in our question. Okay, so if there are n number of components, the sum of the mole fractions will be equal to unity 1. And if there are two components, we can write like chi A plus chi B equal to 1. Clear? Right? Okay. Then next one, we are going to learn about the types of solution, and that's it is affected by lot of factors also. The first one is temperature, next one is nature of gas, and we know that the temperature is affecting the solubility, right? For example, if you are making tea, we add sugar and water, right? And when we are heating it, what will happen? The sugar will easily dissolve in the water. When temperature increases, the dissolution also increases. It will easily dissolve. So there is an effect of temperature on the solubility. Now we are going to learn about the solubility with temperature affecting the gaseous solution. Okay, and also the nature of the gas that we are using. According to the nature of the gas, it will affect the solubility. These things just read, no need, like only the main thing we require is Henry's law. Okay, then nature of the solvent also it will affect. Now we are going to the Henry's law. Henry's law means that, for example, we are having a liquid. We have a liquid. Okay. It is filled with a liquid. Okay, liquid is there. And we are making carbonated drink or 7-Up or Pepsi or something. Okay. Okay, so we are going to mix some gas. Gas is the solute here. Solute means present in lesser quantity. So top portion it will be filled with what? Gas molecules will be there. So gas molecules are present on the top of the liquid. Now what will happen? Whether the gas will dissolve in the liquid? Is it possible to dissolve the gas? How we can dissolve the gas in this liquid? We can apply a pressure on the top of the gas. For example, by using a piston, I am going to apply a pressure P. When I apply a pressure on the top of the gas, what happened to the gas? The gas, liquid is there. Okay, the gas will start to like mix with the liquid and dissolves in the liquid. Why? With the effect of the pressure, the gas will dissolve in the liquid. So you got the idea how we are dissolving the gas in liquid? By applying a pressure on the top layer, what will happen? The gas starts to Yes, it's confused too much that I know. First, we are going to learn about the Henry's law. Okay, so Henry's law, we are mixing gas and liquid, right? So when we apply a pressure, what happened? The gas molecules starts to dissolve in the liquid. Okay. So the gas molecule starts to dissolve in the liquid. So Henry told what? Henry states one law that the partial pressure is directly proportional to the solubility. For example, if you are applying a pressure, what will happen? The solubility increases. If you are applying more pressure, what will happen? The gas will start easily dissolve in the liquid, right? So there is an effect connecting solubility and pressure. Solubility and pressure. That means they are directly proportional. When pressure is increasing, solubility also increases. They are directly proportional. And there are contemporaries of like Henry, that is Dalton. He modified the equation using the mole fraction. Only slight change is there. So what is Henry's law? States that the solubility of gas at a constant temperature is directly proportional to the pressure of the gas. That is very important. It will be asked to like state the Henry's law. And what is the relation between pressure and solubility? What is the relation? And one more thing, why our soda bottles are sealed under high pressure? When we open the bottle caps, what will happen? The juice will come out, right? Why it is coming out? Because the carbon dioxide is filled under high pressure or sealed under high pressure to make the solubility more. So that is the relation here. When we apply pressure on a gas, what will happen? It will easily soluble in the liquid. Got it? So when pressure increases, solubility also increases. They are directly proportional. Solubility is directly proportional to pressure. And Dalton modified the law like, we can write the modified one. Mole fraction. What is mole fraction? The symbol that we use for mole fraction? Chi. Mole fraction is directly proportional to pressure. Okay. Mole fraction is directly proportional to pressure. And we can remove the proportionality. We want to remove the proportionality and we want to make into equal to sign, right? Okay. So we want to make the Dalton's theory. Dalton's atomic theory is not required in class 12. It is already we learned in class 11, right? So P is directly proportional to chi. P means what? Pressure is directly proportional to mole fraction. Chi. Now we are going to remove the proportionality constant using an constant K. Okay, we are going to use a constant K, that is Henry's law constant. Chi directly proportional to P, chi equal to Kh into P. What is Kh? Kh is known as the Henry's law constant. Okay, Henry's law constant. Got it? Kh is known as the Henry's law constant. Why it is Henry's law constant? Because discovered by Henry. That's we are giving the name Kh like Henry's law constant. We remove the proportionality using the Kh. So what is Henry's law? Mole fraction is directly proportional to the pressure. So we can rewrite using the mole fraction. Mole fraction chi directly proportional to P. That means chi equal to Kh into P. Clear? Got it? Any doubt? So, next one, we got the equation like what? P equal to Kh into chi. And again, we can write it like what? In the Henry's law, it is stated that, what is Henry's law? In Henry's law, the pressure is directly proportional to solubility. And Dalton modified it slightly like what? Henry's law, it was like pressure is directly proportional to solubility. When solubility increases, when the pressure is increasing. So when we are applying a high pressure, what will happen to the solubility of gas? The gas will easily dissolve in the liquid. So we are modified like mole fraction. Mole fraction, what is the equation for mole fraction? Chi. Chi is directly proportional to P. So it will be like what? Chi directly proportional to P. And we want to remove the proportionality constant. So to remove the proportionality constant, we are using equal to Kh into chi. Got it? This is the main equation that we are using. P is equal to Kh into chi. Clear? Any doubt? Okay. So P equal to what? Kh into chi. What is Kh? Kh is the Henry's constant, where chi is the mole fraction. And Kh will be different for different gases. Clear? So Kh will be different for different gases. Okay? Clear. Okay, done. Then, Now we are going to learn about the applications of Henry's law. 3 applications are there. First application is that we are using in our daily life, that the carbonated drinks. We are sealing the carbonated drinks under high pressure. Why? That we already discussed. Because to increase the solubility of the carbon dioxide. Carbonated drinks or soda water, like we know 7-Up, Mirinda, like lot of drinks are there. No. So it is sealed under high pressure to increase the solubility. So first application is soft drinks. To make soft drinks, the bottles are sealed under high pressure to increase the solubility of CO2. Clear? So pressure increases, what happened to the solubility? Solubility also increases. Okay, then next one is sea divers. Now, that is very, very important. Like when we are going down under the deep waters, what will happen? The pressure increases, right? If we are going down into the sea, the pressure increases. If pressure increases, what happens? What happens to the gases around us? So the nitrogen, oxygen, lot of gases are there, no? So when gases are there, the solubility of the gases increases when the pressure increases. When we are going down the sea, the pressure increases, so the solubility of gases also increases, note it. So that's why we are using a mixture of oxygen and helium to minimize the painful effect by nitrogen in decomposition. Nitrogen starts to easily dissolve in our blood. Like if you are going down the sea, for example, this is the sea, and if you are going down into the sea, pressure is very high there. Under the sea, the pressure will be very high. So it is very difficult to cope up with the condition. So when pressure increases, the solubility also increases, that we learned. Solubility also increases. So the nitrogen starts to dissolve in our blood. So what happens? More gas will be dissolved in our blood. That's why the divers are carrying a cylinder in the backside. And the cylinder will be mixed with what? Oxygen and helium to minimize the painful effect. It is very dangerous thing. Okay. And that condition, you know what is the name of that condition? One condition is there. What is the name of that condition? Can anyone comment? Is it anoxia or bent? That's a question for you. What happens when the nitrogen start to dissolve in our blood when we go under deep sea, deep level? What happens? The gases start to dissolve easily. So what will happen? No one is replying. So one more condition is that we can learn. Okay. So the opposite. When we are climbing mountains, we are going high altitude. What happened to the pressure? When we are going high altitude, the pressure will decrease. So we won't get enough oxygen at the high altitude. So the oxygen level starts decreasing and we won't get enough oxygen for the respiration purpose. So what will happen? We will fail and we'll get nausea. So it will be completely dangerous for our health. Sometimes blood will come out from our ears and nose. So that time also we will be carrying oxygen cylinders. Clear? So two conditions that we are going to learn is anoxia and bent. Both are very, very harmful for the human health. So that are the application for the Henry's law. Study the 3 application. It is very, very important for your exam. Okay? Clear? Okay. Then next one is vapor pressure. You know what is vapor pressure? That is very important thing that we are going to use till the end of the chapter for the derivation purpose also. We are going to use the vapor pressure. Vapor pressure is the pressure exerted by the vapors. Okay. So for this we can learn like the vapor pressure in equilibrium with the liquid for a given temperature is a pressure forced by the vapors. That means the pressure exerted by the vapors. So we can learn like, for example, there are 2 beakers. Okay. First one is only solvent. What is it? Pure solvent. In other beaker, I took solute and solvent. For example, it can be sugar and water. In the first beaker, only solvent is there. So, only solvent molecules are present. It can be liquid or anything. Only solvent molecules are present. Here, the solvent molecules can easily vaporize, right? Is anyone giving a barrier or hindrance there? No one is giving any barrier or hindrance, right? So, these molecules can what? Easily vaporize or evaporate as molecules. So, it will go like as vapors. So, their vapor pressure will be very high. That is very, very important. For pure solvent, only solvent molecules are there. No one is giving any kind of hindrance or barrier. So, the pure solvent can easily vaporize. So, the vapor pressure of the pure solvent will be very, very high. Okay. Now, next thing. In the next beaker, I took solute and solvent. For example, sugar and water. So, I am going to draw first water molecules. in this I am going to add some sugar or any kind of molecules. So what will happen? The sugar is mixed with water. Can the water easily vaporize? Is it possible? Is it possible? No, right? Why? Because the solute molecules will give a barrier or hindrance on the top layer. This red color molecules are solute molecules. Okay, the solute molecules will give a barrier or hindrance on the top layer. So the solvent cannot easily go as vapors. There will be a hindrance. Hindrance means what? There will be an obstacle. So it won't allow to easily vaporize. So the vapor pressure will start to decrease. So this is the main point. What is vapor pressure? The pressure exerted by the vapors. Okay, it is not possible. Okay. So, in the case of pure solvent, no solute is present, right? So, the solvent can easily vaporize and change into vapor state. So, the vapor pressure will be very high. But in the case of solution, solute and solvent is present. Solute is there, solvent is there. So, solute molecules will be mixed with the solvent molecules. So, solute will slightly hinder the vaporization. So, it will affect the vaporization. Got it? So, solute will give a barrier or a hindrance for the vapor solvent molecules to become vapor. So, the vapor pressure starts to decrease. So, the question is that solute, like solution or solvent will be having more vapor pressure. Can you comment it? Please do the comment. Solute plus solvent or solvent is having more vapor pressure. Which will be having more vapor pressure? Which will be having more vapor pressure? Tell. No one is doing the comment. Which one will be having more vapor pressure? It is written in the board, right? Solvent, right? Pure solvent will be having more vapor pressure. Yes, I will repeat. In the case of pure solvent, only solvent molecules are present, right? No solute molecules, no hindrance, no barrier, no obstacle. So the molecules can easily vaporize. So the vapor pressure will be very high. Got it? But in the case of solution, both solute and solvents are present. So the solute molecules will be mixed with the solvent molecules. Can the solvent easily go? No, right? Look the red color. This red color molecules are mixed with the solvent. So the solute molecules will give a barrier. It won't allow the solvent to go easily. It will give some obstacles. Okay. That case, the vapor pressure starts to decrease. Clear? So solvent will be having more vapor pressure. Solution will be having less vapor pressure. That is the difference. Okay. So related to this, we are going to learn about the colligative properties also. Clear? Okay. Then, with increase in the temperature, the vapor pressure of a liquid increases as kinetic energy of the molecule increases. This one is not required actually, but for your knowledge, I have kept it. Okay. So, the main thing is that, look here, when we are increasing the temperature, what happens? For example, we kept a kettle and added water to it, one bottle of water, and we started to heat it. What will happen? The water will easily vaporize, right? There is no obstacles, no solute, no sugar, no salt. So the water will easily evaporate and we are giving heat, right? We are increasing the temperature also. So what happens? When temperature increases, the vapor pressure also increases. It will easily vaporize. Clear? Got it? So that is the main point. When temperature increases, vapor pressure increases. Learn this. Temperature increases, vapor pressure also increases. Oh, so this is the curve. Look here. It's a curve. Okay. So vapor pressure, temperature curve. Now, to the same kettle, I am going to add sugar, like 5 spoons of sugar. What will happen there? What will happen? It will vaporize easily? No. The molecular mass is increasing, right? Because we added sugar to the water. So the weight increased. So it requires more time to boil and it requires more temperature. So the vapor pressure starts to decrease. That is the difference. Clear? So temperature increases, solubility increases, vapor pressure also increases. Vapor pressure increases. So what happened to the vapor pressure increases? The kinetic energy of the molecules also increases. That means when we are heating, the molecule starts to move very fast. If they are moving very fast, the energy due to the motion, for example, now I am standing still. Is there any energy for me? No, right? Now I am possessing potential energy. The energy due to position that we learned in physics, that the energy due to my position. Now I am having a position that much height from the ground. Now I am standing still here. Now I am having a potential energy. That means the energy due to position. Now I started to move. I am moving forward. I am moving backward. Now I possess one energy. What is energy? The energy due to motion. The energy due to motion. Now moving my hands, I am moving to this side, I am moving front. Now I am possessing one energy, right? This energy is known as kinetic energy. Clear? The energy due to motion is known as kinetic energy. So when we are heating the water or heating the liquid, when temperature increases, what happens? The molecule will start to move fast. They will move fastly. When they move fastly, their kinetic energy, the energy due to motion. The energy due to motion also what? Increases. Kinetic energy increases. So their vapor pressure also increases. Got the relation? Temperature increases, vapor pressure increases, kinetic energy increases. Three things we learned here. Clear? Okay. Now, the vapor pressure of a solution that we now discussed, okay. The pure solvent is added to a miscible solute, then they form a solution. We know how a solution is formed. By mixing a solute and solvent, it will form a solution, right? There is a decrease in escaping tendency of solvent molecules as some molecules of solute replace the molecules of solvent from the surface. This causes the decrease in the vapor pressure. Clear? That we have discussed now using that diagram, that if you are adding a solute to the solvent, what will happen? The surface will be covered with the solute molecules. The solute won't allow the solvent to easily vaporize. So what happened to the vapor pressure? Vapor pressure starts to decrease. Any doubt? Okay. If you are having any doubt, please do the comment so we can clarify the doubt and go forward. Okay. Okay. Clear, right? Set? Okay. Then, vapor pressure of a pure solvent is more than that of solution that we learned now, because in pure solvent, no one is giving any hindrance, no one is giving any barrier. So, the solvent can easily go as vapors. So, the vapor pressure will be very, very high. Okay. So, that is the main difference. Now, we are going to learn the Raoult's law. What is Raoult's law? What is Raoult's law? Raoult's law is like a Henry's law. What is Henry's law? We learned the Henry's law, that is pressure is directly proportional to mole fraction, right? And we modified like Kh into chi, where Kh is known as the Henry's law constant. That was our Henry's law. Now we are going to learn about our Raoult's law. What is Raoult's law? Right. Raoult's law for volatile solution, it states that Raoult's law is very, very important, and the law is that the vapor pressure of the component for a given temperature is equal to the multiplication of mole fraction of the component in the solution and vapor pressure of the component. That means like the vapor pressure P equal to vapor pressure of pure solvent into mole fraction. Chi 1. Just I wrote 1 because there will be many components. Okay, no need to look this equation. Just learn this Raoult's law. So what is Raoult's law? Raoult's law states that the vapor pressure of a component for a given temperature is equal to the mole fraction of the component and vapor pressure of the component in pure state. Okay, wait. Vapor pressure, we can denote it by P. Vapor pressure of pure solvent we can denote using P naught, and mole fraction is what? Chi. Mole fraction is chi. And according to Raoult's law, what is Raoult's law? According to the Raoult's law, the mole fraction, the vapor pressure P is given by multiplicating the vapor pressure of pure solvent and mole fraction. P naught into chi. For example, there is one component, we can write P1 equal to P10 chi 1. If it is 2, how we will write? P2 equal to the vapor pressure of component 2 is given by P2 equal to chi 2 P20 chi 2, like this. Clear? Got it? So, if there are n number of components also, we can write a Raoult's law like Raoult's law. What is Raoult's law? The vapor pressure is equal to pure solvent vapor pressure into mole fraction P10 into chi 1. P2 means P20 into chi 2. Got it? Any doubt? So, this is the Raoult's law, very, very important one. Okay. Now, Raoult's law for non-volatile solutes. Raoult's law states that the relative lowering of vapor pressure of a solution containing a non-volatile solute is equal to the mole fraction of the solute in the solution. This equation that we will learn in the relative lowering of vapor pressure that we are going to derive now. Okay. So, before that, we should know what is ideal solution, what is non-ideal solution. Any solution that obeys Raoult's law, Very easy thing to learn. Ideal solution means any solution that obeys Raoult's law in all the means which obeys Raoult's law are known as ideal solution. Clear? In which ideal solution means that will obey Raoult's law. And one more thing is that if it is obeying Raoult's law, the delta H mix, the enthalpy, there won't be any enthalpy change, it will be equal to 0. If you are mixing two components, there won't be any what? Okay. I'm not going in speed, okay, I'm slow down. Okay, done. We can go slowly. Okay, listen here. Ideal solution means which does not obey Raoult's law. Okay, which obeys Raoult's law, not does not, which obeys Raoult's law in all means. That means if you are mixing two solution or mixing two components like a solute and solvent, when we are mixing, there won't be any change in the volume. For example, if you are mixing 20 ml of juice and 10 ml of water, what will be the total volume? Can you tell? I am going to mix 10 ml of water and 20 ml of juice. What will be the volume? Tell. What will be the total volume? If I am mixing 20 ml of juice and 10 ml of water, what will be the total volume? It will be 30 ml, no? There is no change in the volume. It is not decreased, it is not increased. There won't be any change in the volume. If it is like that, it will be an ideal solution. The delta V mix equal to 0. No change in volume, no change in enthalpy while mixing. Okay, so for mixing or yes, very good, 30, there won't be any change, right? If there is no change, that kind of solutions are known as ideal solution. And in the case of ideal solution, solute-solute, solvent-solvent interactions are similar to solute-solvent interaction. That means, for example, like we are mixing, solute is there, solute name is A, solvent name is B. And we are mixing both solute and solvent, we are mixing. So there are a lot of molecules will be there. So in this beaker, like we can mark like red color is solute, red is solute, and blue is solvent. Okay, so two different types of molecules are there. Okay, two types of molecules are there. Here there will be an interaction, right, between solvent. Already there will be an interaction. If water is there, there will be interaction between water molecules, we know. If sugar molecules are there, sugar molecules will be having an interaction. Like that, here, this blue, there will be an interaction between them. These blue, there will be an interactions, right? Like that, these red molecules also will be having an interaction between them. So blue, red. That means solute interaction is there, solvent interaction is there, and when they starts to mix, there will be an interaction between solute and solvent. Clear? So, solute interaction, solvent interaction, and solute-solvent interaction will be same. There won't be any difference between the interaction. So, we can simply write like A. We can give a simple explanation like here A is there, B is there. AA interaction is there, BB interaction is there, and AB interaction. What is AA interaction? Solute interaction, solvent interaction, and solute-solvent interaction will be same. That's why the enthalpy change is not equal to 0, then is equal to 0, then volume change is equal to 0. There won't be any change in the enthalpy of mixing and volume of mixing. It is same. Yes, we will do organic also. Okay, by after completing this chapter, we'll be going to organic also. Okay. Clear, right? Okay. So, in the case of ideal solution, learn the main point that solute, solvent, and solute-solvent interactions are almost similar. There won't be any difference. That is delta V equal to 0, delta H is equal to 0. Clear? Then, next one, we are going to non-ideal solution. Example, these examples are very important and it is asked for a MCQ question for the previous board exams. Okay, which solutions will show, okay, which solutions will show this ideal behavior, like the mixture of benzene and toluene, hexene, heptane, ethyl bromide, ethyl iodide, chlorobenzene, bromobenzene. Learn 3 or 4. Okay, so it is very, very important. Learn these examples. And the graph is shown here. Graph, look here. This axis shows the vapor pressure, and this one shows mole fraction. Okay, this one shows mole fraction. And first one, this is the vapor pressure, like mole fraction to give. This axis is given the component A, this one component B, and their total is given P total. P total is given by the pressure of PA plus PB. What will be the total pressure? Component A plus component B. Only that much. Okay. Clear? So it will be a case of straight line. Then next one is non-ideal solution. Okay, non-ideal solution, just the opposite of ideal solution. Like almost all the solutions are non-ideal. No one is like ideal. So ideal is an imaginary concept, but non-ideal, majority of the solutions are what? Non-ideal solutions. So non-ideal means which does not obey Raoult's law in any means. Which does not obey Raoult's law. Okay, that's the first point. Does not obey Raoult's law, and while mixing, the volume can be high or low, enthalpy can be positive or negative. There will be difference. Okay, so delta V mix not equal to 0, delta H mix not equal to 0. That means the solute-solvent interaction. Solute-solute is there. We can write solute-solute how? AA interaction, then BB interaction, and AB interactions will be there. No, that solute-solvent interactions are different from solute-solute and solvent-solvent interaction. Both are different. Okay, there will be interaction between solute-solute, solvent-solvent, and solute and solvent. They won't be equal like the ideal solution. In ideal solution, they are equal, right? AA interaction equal to BB interaction equal to AA interaction equal to BB interaction equal to AB interaction. Both are almost same. But in the case of non-ideal solution, they won't be same. Solute-solute, solvent-solvent, and solute-solvent interactions are not same. Okay, that's why their mixing is not equal to 0, volume mixing is not equal to 0, and enthalpy mixing is not equal to 0. And if it is high, there are again two types of classification, positive deviation and negative deviation, and it's very, very important for your exam. Okay, so we can discuss the positive deviation. Positive deviation means the vapor pressure, the total vapor pressure is more. Positive means what? More than the expected value. There will be an expected value, no. Than the expected value, the vapor pressure will be more, then that solution is known as positive deviation. The solution showing positive deviation and expected to the Raoult's law. Then this happens when a new interactions are weaker than the interactions in the pure component. That means AA interaction, BB interactions will be there. AB interaction will be less than AA or BB. Note that solute-solvent interactions are weaker here than AA and BB interaction. Solute-solvent interactions are weaker than solute-solute, solvent-solvent interactions. And in the case, vapor pressure will be higher than the expected value. Higher means it will show the positive value. Okay, clear? So it will show the positive value. Why? Because the vapor pressure will be very high than the expected value, and this happens when AB interaction, solute-solvent interactions are lesser than solute-solute, solvent-solvent interaction. Okay. Then we are going to derive the equation, and here the delta H is positive, delta V is also positive, entropy also positive, everything will be positive. That's why it is known as what? Positive interaction. Okay, got it? Then examples are acetone carbon disulfide, mixture of acetone and carbon disulfide. It's a previous year MCQ question which shows a positive deviation. Acetone and carbon disulfide, then acetone benzene, carbon tetrachloride chloroform, methyl alcohol water, acetone and ethanol. And in the graph, it won't be straight like the previous one. For the ideal solution, it was a straight line graph, right? But here, look here, the graph will be like this was the pressure of first component, B component, A component, and there is a increase in the curve. Look here, the red color. The curve increases because the partial pressure, the vapor pressure increased. The vapor pressure is increasing. Here also the pressure is increasing. So the total one will be what? Actually, this is the total one line. That also it is different. It is increased like this. The P total is greater. Actually, For example, for PA we can write like according to the Raoult's law, what was the equation? P1 equal to P10 chi 1. So we can write PA equal to PA0 chi A, PB equal to PB0 chi B. This was the two equation. And how we will write the total equation? The P total. P total is given by P total equal to PA plus PE. First learn this, okay. The total pressure is given, the total vapor pressure is given by the vapor pressure of the individual one, PA plus PB. And we know the equation for PA and PB. What is PA? PA0 chi A, PB is PB0 chi B. Okay. Clear? Got it? Then. Now, according to the non-ideal solution posterior deviation, when we add the two values, it will be higher. To show that it is higher, and we know the graph, the original graph was like this. First component, we can write A component, this one B component, and total one P equal to PA plus PB. And this was the ideal solutions graph. But when it is high, what will happen to the graph? It will show slight deviation. It will be high. This curve also it will be very high, and this will also very high, like this. It will increase. Okay? Got it? Now, we can go to the other one, that is negative deviation. Negative deviation is very, very easy now. We already learned positive deviation. Positive deviation means what? The vapor pressure will be very high than the expected value. When the vapor pressure is very high, it will show positive deviation. AB interactions are weaker than AA interaction and BB interaction. Then the next one is negative deviation. Negative deviation just opposite. Vapor pressure will be what? Vapor pressure will be low. Okay, in the case of negative deviation, the vapor pressure will be less than the expected value according to the Raoult's law. When the vapor pressure is low, we can write like AB interaction. What is AB interaction? We know for making a solution, there will be solute and solvent, right? Solute will be there, solvent will be there. When solute and solvent together mixes, it will form a solution. So solute, we can write A. Solvent is B. They will form an interaction, that is AA interaction is there, BB interaction is there, and they will mix together. So they will have an interaction like AB interaction is also there, right? So in the case of negative deviation, the AB interactions are very high. AB interactions are higher than AA interaction. Got it? Clear? So in AB interactions are greater than AA interaction and BB interaction. So that's why they are showing a negative deviation. What was the Raoult's law? According to the Raoult's law, the vapor pressure is given by PA0 into chi A. PB equal to PB0 into chi B. And the total will be the sum of PA and PB. And the some value will be less than the expected value. The vapor pressure will be less than. So we can draw the graph like this. The graph is like here vapor pressure is there, mole fraction in this axis, and two components. This one B component, this one A component. Now the total will be here. Once more again I will draw here. A component, B component, then total. Then total value will be less. To show that, we can draw a curve like this down. And this value will be decreasing. This also will be decreasing. To show that, we should draw a curve like this. Okay? Clear? So, this was the graph for the non-ideal solution. Look here. So, vapor pressure is here, mole fraction is here. Actually, it was a straight line for the ideal solution. But if it is non-ideal solution showing a negative deviation, the vapor pressure value is decreasing than the expected value of Raoult's law. So, while drawing the graph, this will be decreasing like this. This curve also we should draw down the straight line. Then only it will be showing the decreasing. Okay, got it? Okay. Now, the example showing the negative deviation are chloroform and benzene, and this was the previous question. Chloroform and benzene, the mixture of chloroform and benzene shows a negative deviation. That means the delta V mixing is not equal to 0. Then delta H mixing not equal to 0. It will be having a negative value. Then nitric acid and water, acetic acid and pyridine. These are the 4 examples for negative deviation. Non-ideal solution showing negative deviation. Is that clear? Okay. Then next one is azeotropic mixture, and azeotropic mixture is also a previous year question for 2 marks for our board exam. Azeotropic mixture means when we are mixing two liquids having same boiling point, because of the same boiling point, the two liquids cannot be separated. Got it? We are mixing two liquids. There will be two liquids. Okay. And we are mixing the two liquids. Just consider just an example like two liquids are there. One glass of one liquid and other glass of other liquid. And we are mixing the two liquids. What will happen if they are having same boiling point? If they are having different boiling point, we can just heat it. One will be easily vaporized, right? The boiling point high, it will be vaporized, and so we can separate the other one. But here, is it possible? No, right? If we are mixing two liquids, with same boiling point, it is not possible to separate the two liquids. Why? Because they are having the same boiling point. Clear? Okay. They are having the same boiling point. Because of the same boiling point, they are unable to separate using the fractional simple distillation method. And we can use the high fractional distillation method to separate them, but it is difficult to use the fractional distillation to separate the mixtures because they have the same boiling point. And these mixtures are called constant boiling mixtures formed by non-ideal solution. Actually, these words are not required. It's not in our textbook. You can read, but just learn what is azeotropic mixture. Okay, so what is azeotropic mixture? If you are mixing two liquids having the same boiling point, because of the same boiling point, these two liquids cannot be separated. Okay. Then, Raoult's law that we already discussed, Henry's law, Raoult's law. Then, types of azeotropic mixture. There are two types of azeotropic mixture. The first one is what? Azeotropic mixture with minimum boiling point. Can you tell what is minimum boiling point? Azeotropic mixture is a mixture of two liquids in which the boiling point of mixture is less than either of the pure components. Mixture is less than either of the two pure components. If you are taking the two pure components and mixing it, it will form a solution, right? So, the two pure components boiling point, that mixture, after mixing their liquids, boiling point will be less than the pure solvent. For example, two beakers, component A is there, B is there. And when we mix, it will form AB. AB boiling point will be less than A and B. Clear? Okay, the AB boiling point will be less than A and B. That means the minimum boiling point, the mixture of two liquids in which the boiling point of mixture means A and B. A and B are the two components, and A will be having one boiling point and B is having the other boiling point, right? So, after mixing, AB boiling point will be less than A and B. Okay. Then, and it is formed by the composition of non-ideal solution which shows positive deviation of the solution having maximum vapor pressure, and it's like an opposite. Minimum boiling point is shown by positive, minimum positive. So, maximum will be shown by what? Like negative deviation. Two cases are there. We learned about positive deviation and negative deviation, right? Positive deviation is showed by minimum boiling point, and maximum boiling point is showed by negative deviation. Two cases, just opposite. Again, we can discuss about the azeotropic. Azeotropic mixture with minimum boiling point means the mixture will be having less boiling point than the pure one. AB is less than A and B. And it is showed by positive deviation solutions. Positive deviation solutions. Okay. Then, next one. It is formed by the composition of non-ideal solution showing positive deviation to the solution having maximum vapor pressure. So, these 2 points are very important. Okay. Then, next one, the mixture consists non-ideal solution showing positive deviation Raoult's law, and for which the vapor pressure is maximum. Examples are given. Mixture, this is very, very important. Note it. Okay. Mixture of ethanol and water, and like the mixture ethanol and boils at 95.5% ethanol and 4.5% water. It boils at 35.5 Kelvin. Now, the boiling point of ethanol is 78.1. Boiling point of water is 100 degrees Celsius. Okay. Then, next one is azeotropic with maximum boiling point. Maximum boiling points with Two components means when we are mixing two components, their boiling point of mixture will be larger than. That means AB boiling point will be greater than A and B. The boiling point of A and B will be greater than A and B. Okay, got it? Two types are there, minimum boiling point and maximum boiling point. Minimum means the AB boiling point will be less than the interactions are there, no. That AB boiling point will be less than A and B. In the case of maximum boiling point, the AB boiling point is greater than both the pure components A and B. AB is greater than A and B. And it is showed by non-ideal solution showing negative deviation. Minimum showed by maximum, that is minimum by positive and maximum by negative, just opposite, okay. Minimum by positive and maximum by negative. Mic is not working, you cannot hear? Okay, I will change it, okay. Wait a minute. Just tell, is it okay now? Is it okay? Is it audible now? Now is it okay? My dear? Okay, right? Can I continue? Okay, done. Okay. And the examples are nitric acid and water. Mixture boils at 393.5 Kelvin and aqueous solution of HCl, pure water. Okay, so just learn one example for the azeotropic distillate maximum and minimum. Okay. Next one, we are going to the main session of this chapter, that is colligative property, and we want to learn about the four colligative property. What is colligative property? Colligative property depends upon only the number of the solute particles. Okay, colligative property means it depends upon only the number of the solute particles, the number of particles like molecules or ions in the solute, and it defines the amount of the solvent but not on the nature of the solute, and it is termed as colligative property. And there are four colligative properties that we want to learn, that is relative lowering of vapor pressure, osmotic pressure, elevation and boiling point, depression in the freezing point. Okay, so there are four colligative properties, and colligative property means what? The properties of solution, that is very important. Note the properties of the solution that depends upon only on the number of the solute particles. Solute particles, that means molecules, ions, anything. Okay, only depends upon the solute particles. And from that we are going to learn the first derivation, that is relative lowering of vapor pressure. Relative lowering of vapor pressure. Okay, so can we start? First one, relative lowering of vapor pressure. When will the vapor pressure decrease? We already learned in the beginning itself that if you are taking two beakers, one only with water, one with sugar and water, which will be having more vapor pressure? Who will comment the answer? That's very easy. We are taking two beakers, one with only water and the other with water and sugar. Which will be having more vapor pressure? Which will be having less vapor pressure? Which will be having more vapor pressure and which will be having less vapor pressure? Tell. No one is telling the answer. No one is saying the answer. Why? What happened? We already discussed it many times. No. So look here. We are having two beakers. One beaker only with pure solvent, other with solution. That means two types of molecules will be there. Both like solute molecules are there and solvent molecules are also there. But here in the case only solvent is there. So no one is giving any kind of hindrance. What will happen? Yes. Very good. So in the case of pure solvent, it can easily vaporize. No one is giving the hindrance or barrier for the vaporization. Yes, water will have high vapor pressure. Yes, very good. Why? What is the reason? Because no one is giving any barrier here, right? So it can easily vaporize. So the vapor pressure will be very high here. But in the case of solution, solute molecules are also present along with the solvent molecules. So when solute is present along with the solvent molecules, the solute will be present on the top layer. It won't allow the solvent to vaporize. So the vapor pressure starts to decrease. That is the relative lowering of vapor pressure. Clear? So for the solution, the vapor pressure starts to decrease. Lower the vapor pressure decreases. Clear? So consider the two things. One is pure solvent and other is the solution. For the case of solvent, pure solvent, the solutions, there is no solute to hinder the vaporization. Okay. Okay, so the solvent molecules easily vaporize, vapor pressure will be very high. But in the case of solution, both molecules are there, so it won't be easy to vaporize. So vapor pressure starts to decrease. Okay, so we can take P0, P0 as the vapor pressure of the pure solvent. This not like raised to 0, no. This will be always for pure. P0 is the vapor pressure of the pure solvent. P is the vapor pressure of the solvent in solution. And the lowering of vapor pressure we can write like, we are going to derive the equation, very important one. P0 is the vapor pressure of pure solvent. Vapor pressure of pure solvent. Next one is P. P is the vapor pressure of solution. We can write like vapor pressure of solution. Okay. That means vapor pressure of solvent in solution. Now we are going to write the difference in the vapor pressure. Delta P. How we will write the delta P? Delta P is the change in vapor pressure. The change in vapor pressure greater one minus lesser one. Which is the greater one here? P0. So we can substitute like delta P equal to P0 minus P, equation number 1, very important. What is delta P? The change in the vapor pressure is given by vapor pressure of pure solvent minus vapor pressure of solution. Clear? So this was the first equation, give equation number 1. Okay, then next one. Divide the whole term with P0. What we want to do? Take the equation, divide the whole terms with P0. What is P0? Vapor pressure of pure solvent. So what will happen here? We can write like the delta P divided by P0 equal to P0 minus P divided by P0 or P naught. You can call it as P naught also. Okay. Delta P divided by P0 equal to P0 minus P divided by P0. And this is known as the relative lowering of vapor pressure equation. What is the equation? Delta P by P0 is equal to P0 minus P by P0 equal to relative lowering of vapor pressure. Okay. Now, when a solution is prepared by mixing two non-volatile solute B and A, what will be the mole fraction? Chi A and Chi B the mole fraction, and Chi A plus Chi B equal to 1, and we can write Chi B equal to 1 minus Chi A. Okay, so we can rewrite the equation like, we got P0 minus P divided by P0 is equal to what? Delta P divided by P0 equal to what we got? Chi B, Chi A and Chi B. Okay. Chi. What is chi? If it is chi A, we can write here A. So chi A, we can rewrite like Na by Na plus Nb. Na by Na plus Nb. And here Nb is very small. When Nb is very small compared to Na, we can neglect the Nb. So the final equation will be like P0 minus P divided by P0 equal to Na divided by Nb. What is Na divided by Nb? Number of moles of A divided by S mole fraction. Okay. So number of moles of A divided by number of moles of B. Clear? Got it? So what is the equation for relative lowering of vapor pressure? Vapor pressure P0 minus P divided by P0 equal to Na divided by Nb. Na divided by Na plus Nb was there, but Nb is very small. than Na, so we can neglect the Nb term, so only Nb will be there, so Na divided by Nb we will get. So what is Na? It is the number of moles of A divided by number of moles of B. Then again we can rewrite like Wa by Ma divided by Wb by Mb. What is Wb? Ma? Wa means weight divided by molar mass. Weight of B divided by molar mass of B. This is the final equation for the relative lowering of vapor pressure. Okay. So, our Xb is a mole fraction of the solute. So, we are giving Xb as a mole fraction. We can give X or B. Okay. So, this is the final equation. Learn this for the vapor pressure of the relative lowering of the vapor pressure equation. Okay. Got it? P0 minus P divided by P0 is equal to Na divided by Nb equal to, we can again substitute the equation for the number of moles, Wa divided by Ma divided by W divided by Mb. Clear? Okay. The next one is elevation and boiling point. And this is very important next colligative property. Elevation and boiling point means, listen, for example, if you are adding solute to solvent, what happened to the boiling point? Boiling point increases, right? The boiling point will increase. Why? Because the molecular mass is increasing. If there is only solvent, no problem. If you are making tea, what will happen? We will add salt or sugar. Not salt, we will add sugar, we will add water, we will add tea leaves, everything we will add and we will heat it, right? When we heat it, it will take longer time than the water. If there is only water, it will easily vaporize, it will boil easily. But in the case of adding sugar or other particles, it will take more time. Why? The molecular mass is increasing. So you got the point. What is elevation and boiling point? When we compare the pure solvent and solution, pure solvent will be having more boiling point. Na missing. Where Na missing? You're telling about the previous equation. Nb is missing. Okay, not Na. Na divided by Nb because Nb wait, I will explain it again. This one you are asking, no. When we compare the two one, Nb and Na, the solute will be very less than. For example, if it is solute and B is solvent, the solvent is very greater, no? Again, it is cracking. Now it is okay, right? When we compare Na and Nb, solute will be less and solvent will be more. So, it will be greater, like Na is greater, Na is less than Nb or Nb is greater than Na. So, we can neglect the Na from the denominator. So, we will write Na divided by Nb. In like maths, we are neglecting some terms if it is very small. No, like that, Nb is greater than Na, so we can neglect the Na. That's why. Okay. So come back to the boiling point. In the case of boiling point, pure solvent boiling point will be very high. Look here, look at the graph. The solvent is very high. It is like very high than the solution. Why? In the case of solution, solute is also now also the voice is cracking. Is it okay? Okay, done. So, in the case of solute and solution, when we add solute or solvent, it become a solution. The boiling point will increase. Why? Because the solute molecular mass is very high, so the solution's mass will be very high. So, more time is required for the boiling purpose. The boiling point, more temperature is required, so it will be very low than the solvent. Okay. So, when we compare the solute, solution means what? Solute and solvent. solute and solvent, and only solvent is there, right? Okay, so only solvent means only water. Just take the example of water. Only water is there. So water can easily boil. No one is hindering the the evaporation purpose, right? And it can easily boil. So the boiling point will be very high for the pure solvent. When we are taking the solution, solute is that, solvent is that, the mass is very high. So it requires more time. So the boiling point will decrease. So from this we can make an equation. The boiling point of temperature of a liquid which its vapor pressure becomes equal to the atmospheric pressure. What is boiling point? It is the temperature at which the vapor pressure becomes equal to the atmospheric pressure. Wait a minute, okay. Now is it okay? Just check. Is it okay now? Done, right? Okay. So, in the case of solute and solvent, the boiling point will be less than the pure solvent. Okay. So, we can write the equation like the elevation in the boiling point is also termed as ebullioscopy, that we will learn ebullioscopic constant is there. Okay, so before that it is denoted by delta TB. Delta TB equal to, delta TB is the difference in the boiling point, which will be having high boiling point for pure solvent. So we will mark TB 0 minus TB. Every 0 will be for the pure solvent. Okay, delta TB equal to TB 0 minus TB. TB 0 means for pure solvent. TB is for solution. Solution is having less boiling point. So we made an equation like delta TB equal to TB 0 minus TB. Okay, then delta TB is known as the elevation, that increase in the boiling point of solvent due to the addition of non-volatile denoted by delta TB, and delta TB is directly proportional to the molarity M. Okay. Delta TB is directly proportional to the molarity small letter m. Okay. Now, we can substitute here delta TB. We want to remove the proportionality by using a constant, that is Kb into m, where Kb is known as the elevation in the boiling point or ebullioscopic constant. Very, very important thing. Delta TB equal to Kb into m. Now we can write the substitute the equation for m. What is m? Molarity is equal to number of moles of the solute, right? Number of moles of solute divided by mass of solvent in kilogram. Solvent in kilogram. This is the final equation for delta TB. Okay, so delta TB directly proportional molarity. To remove the proportionality constant, we introduce the constant, that is Kb, known as ebullioscopic constant or boiling point elevation constant Kb. Kb into m, Kb into number of moles of solute divided by mass of the solvent in kilogram. Okay, so it will become like this. This is the final equation. Delta TB equal to Kb into volume. That means number of moles of the solute, right? W whole divided by m into mass of the solvent in kilogram. That means W into 1000. Okay. So both are different. This is for B and this is for A. A is solvent and B is solute. Okay, clear? So learn that equation. That will be very, very useful for you. Delta TB. Sometimes the question is to find the delta TB. Sometimes it will be for elevation KB. So just interchange the terms. Take AB to the other side, TB to the opposite side. You can make the other equation also. So what is weight? Weight of the solvent is there. Weight of the solute is there. Here it is weight of solute. Down it will be weight of solvent. M is the molecular mass and Kb is the molar elevation constant or ebullioscopic constant. Very, very important. Molar elevation constant or ebullioscopic constant. Then Next one, next colligative property is depression. Depression and freezing point, same thing, which takes more time for freezing. Just look the graph. Solvent is there, solution is there. If only water is there and we have water is there, it will easily freeze, right? Right? Then, if you are adding sugar or if we are taking a like ice cream, what will happen? It's become a solution, right? Two components are there. So if it is a solution, it will take more time for freezing. So what is freezing point? Freezing point is the same solid and liquid forms an equilibrium having the same vapor pressure. Okay. So which will be having the more freezing point? Can anyone tell? We can denote freezing like TF. Which will be having? We should be having pure solvent minus. We should be having more freezing point. Decrease in the freezing point of a solvent due to the addition of a non-volatile solute. That means if you are adding a solute to the solution. That means if you are adding a solute. If you are adding a solute to solvent, what will happen to the freezing point? Freezing point starts to decrease. If there is only solvent, it will easily freeze, right? So, if you are adding a solute to solvent, the freezing point will decrease. Okay. So, freezing point will be low. Okay. For the solution. The decrease in the freezing point of a solvent due to the addition of a non-volatile solute, this is known as cryoscopy. Other one was ebullioscopy and this one was what? Cryoscopy. WA should be molar mass of solute. No. Weight of the solute. A is solvent, B is solute. Okay, don't change. A is solvent, B is solute. Okay. So, we can write the equation like delta TF is equal to freezing point of pure solvent minus freezing point of solution. And the same thing, the delta TF is directly proportional to delta TF is directly proportional to molarity. To remove the proportionality constant, we can introduce a constant that is Kf into M, where Kf is known as the cryoscopic constant or depression. What kind of depression? Molar depression constant or cryoscopic constant. Depression in freezing point. Now, we want to introduce the equation for the molarity, that is delta TF is equal to, if you are having the doubt, the same equation we are using here, okay. So, Kf, what is molarity equation? W divided by M, molar mass. I am writing here B, okay, for solute. WA into 1000 kilogram. To show that is in kilogram, we are using the 1000. Okay, got it? So, it's a final equation delta TF equal to Kf into WB divided by M into WA into 1000. Okay. So, the last colligative property is osmosis, and we are familiar with the osmosis, right? What is osmosis? The movement of what? Net flow of solvent molecules from less concentration to more concentrated solution, or from the solvent to the solution, or across a semi-permeable membrane is known as osmosis. For example, if you are keeping raisins in water, what will happen? It will swell, right? What happen? It will swell. And what will happen if you are keeping mangoes in salt water? It will shrink, right? So, what is happening there? There is osmosis. So, osmosis means the flow of solvent molecules from less concentration to higher concentration. Flow of solvent molecules from less concentration to higher concentration through a SPM. What is SPM? Semi-permeable membrane. Through SPM, semi-permeable membrane. And osmosis was first observed by A.B. Notley in 1748, and it was like absorption of water from soil from the cell walls of roots, water movement from root to upper parts of the plant. These are the examples for osmosis. Okay. Now, when the column is formed as a result of osmosis, then the equilibrium hydrostatic pressure is known as osmotic pressure. To restrict the entry of the solvent into the solution through SPM, the minimum pressure that is to be applied on the solution side is known as osmotic pressure. Before that, this is the SPM. You know what is SPM? SPM is a semi-permeable membrane made up of pig's bladder or parchment paper that will be having small holes. It will allow only the passage of solvent molecules and it will hinder the passage of solute molecules. Solute cannot pass through it. solute cannot pass through SPM because the holes are very, very small, minute holes. Microscopic holes. Okay. And it's made up of pig's bladder or parchment paper, cellophane, like lot of examples are there. Got it? So, it will allow only the passage of solvent molecules. For example, if you are taking solution here, what is solution? Solution is solvent plus solute. Only solvent molecules can pass through this. Okay, here we are taking solvent molecules. So according to the osmosis, what is happening here? The solvent molecules will pass through the SPM to the solution side from lesser concentration to higher concentration, that is osmosis. And we can prevent the flow of the solvent to the solution side by applying a pressure on the solution side. That is known as osmotic pressure. What is osmotic pressure? The excess pressure applied on the solution side to prevent the flow of solution. To prevent the flow of solvent to the solution side. After attaining an equilibrium, we can stop the flow by applying an extra pressure, that is known as osmotic pressure, on the solution side to prevent the flow of solvent. Okay. Okay. So, we can apply a pressure that can be applied on the solution to stop the flow of solvent is known as osmotic pressure. So, what is osmotic pressure? That can be asked for 1 mark. What is osmotic pressure? The minimum pressure applied on the solution side to stop the flow of the solvent is known as osmotic pressure, and it can be denoted by P or like pi, eta. Okay. Okay. Clear? Then eta equal to CST or in our textbook it is like CRT also we can use. CRT, eta equal to CRT, where eta is the osmotic pressure and C is the concentration of the solution, T is the temperature, and what is R? R is, we know the constant like universal gas constant, all the things that we know. Okay. So this is the equation for osmotic pressure, and we can rewrite the equation like eta equal to N by V. The concentration can be changed in N by V terms, N by V into RT. Then take the V to the left side. So V into pi equal to nRT. V into pi equal to nRT is the final equation that we use to calculate the osmotic pressure. Okay, then again we know the N, what is N? Number of moles. Number of moles can be substituted like V pi or V theta. V theta is equal to eta. V eta is equal to number of moles, that is W by M into RT. W by M into RT is the final equation. Next one is determination of molecular weight from the osmotic pressure, and we can determine the osmotic like molecular weight from the osmotic pressure. Okay. I am not ignoring your comment. We will do the numericals after completing this chapter in another live. Okay. Is that okay? So because lot of numericals are coming from the section like only from the colligative properties, that we can do as another live. Okay. So we can calculate the molecular mass, and this is the main application for the osmotic pressure. We can calculate the molecular mass of the polymers, biomolecules. Okay. So the equation is M is equal to W into RT. Instead of S, we can write M is equal to W into RT by eta into V is the equation to calculate the molecular mass. Okay, molecular mass from the osmotic pressure. And accurate molecular weight is obtained under the following condition. The solution must be very dilute, solute must be non-volatile, and solute should not undergo dissociation or association. These are the conditions to calculate the molecular weight. Okay. And when height is involved, then eta is equal to HDG. This is not required for us. This is for the higher competitive exams. So, then isotonic solution, hypotonic solution, and hypertonic solution. There are three types of solution. When the solution is having equal concentration or equal osmotic pressure, like if we are taking two solutions, and semi-permeable membrane is also there, just think about it. Like if the two solutions are having same pressure, whether the solvent will flow from one to the other, from less to higher or high to lower, it will flow? No, right? Why? If the two solutions are having the same osmotic pressure, there won't be any flow. Okay. Okay. So, If the two solutions are having the same osmotic pressure, there won't be any flow. That kind of liquids or solutions are known as isotonic solution. And its example is, and it's a previous year question, 0.9% solution of aqueous NaCl with human RBC. Okay. So what will happen if it is less than 0.9%? If we are taking like NaCl, sodium chloride, less than 0.9%, so what will happen? Or greater than 0.9%, there will happen what? The flow. The cells will shrink and the cells will swell. There are the two conditions. Okay, so first one is, when RBCs are placed in distilled water, that is hypotonic medium, they will swell. If the RBCs are placed in distilled water, that is hypotonic distilled water, the cells will swell. It will swell. And the water will flow into them. Water will flow into them if you are placing it in distilled water. Okay. Why? Because higher to lower concentration. Then, but when they are taken in 5% NaCl, what will happen? Why 5% NaCl? More concentration of NaCl and it will shrink. The cells will shrink. Why? Because the water comes out from the cell. So, three types are there. Isotonic, both concentration will be same. There won't be any flow. Then hypotonic is there, hypertonic is there. Hypotonic means like less concentration. Then higher concentration of NaCl, it will be like hypertonic. The cells will shrink. Okay, clear? So read about this. This is very important. 1 mark question can be asked from this. Iso, hyper, hypotonic solutions. So colligative properties are over. Then the last one is Van Howe factor. Van Howe factor. Okay. So Van Howe factor is what? Sometimes we will be getting the colligative properties and it won't be the correct expected value. There will be some difference in the colligative values that we are getting. So when solute undergo dissociation or association in the solution, they show abnormal molecular masses. There will be abnormality in the molecular masses. If the solute is dissolving or like associating with the solvent in the solution, they will show some abnormality in the molecular masses, and that is calculated by a factor known as Van Howe factor and is explained with the Van Howe factor. Due to this, colligative property become abnormal. If there is any abnormality, the colligative property will also become abnormal. No. So that abnormality is calculated using the Van Howe factor. Okay. Okay, then I is given by normal molar mass divided by observed molar mass. There will be normal molar mass, no. And the mass that we are getting for the extra, that is observed molar mass. I is given by normal molar mass divided by observed molar mass. I equal to observed colligative property or normal colligative property. These three equation we can use 3RC. Okay, then last one is actual number of particles divided by expected number of particles. So, there will be a abnormality. There will be an abnormality. That abnormality can be calculated using the equation normal molar mass divided by observed molar mass. Then, or normal colligative property by normal colligative property observed by normal. Then, actual by expected. For solute showing dissociation, that is very, very important for your MCQ. If the value is greater than 1, it will be showing dissociation. If the Van Howe factor, we are getting the value greater than 1. I greater than 1, it will show, solute will show dissociation. Solute will show dissociation. Okay. Then, if I is greater than 1, the solute will show dissociation. And the solute showing association, I will be less than 1. If I is less than 1, the solute will show association, that is dimerization of acid. Examples are dimerization of acid like benzoic acid and benzene. Okay, dimerization of acids like benzoic acid in benzene. And if the solute is neither showing association or dissociation, then the Van Howe factor, it is be equal to I equal to 1. If neither association or dissociation is happening, the Van Howe factor I will be equal to 1. And for the example is urea, glucose and sucrose. Urea, glucose and sucrose. Okay, clear? Then, and we can calculate the dissociation or association using the equation, the degree of dissociation alpha is equal to I minus 1 by n minus 1. What is the equation? I minus 1 by n minus 1. Degree of dissociation is very, very important equation. Degree of dissociation can be calculated by alpha equal to I minus 1 divided by n minus 1 and alpha equal to I minus divided by n minus 1. From this, what is n? N is the number of species formed after the association. N is the number of species formed after the dissociation. Okay. If it is equal to 1, there won't be any association or dissociation. Neither association, neither dissociation. If it is greater than 1, what is happening? Look here. If I is less than 1, association. If I is greater than 1, dissociation. If no dissociation, no association, I will be equal to 1. No association or no dissociation. Okay. No dissociation, no association, I is equal to 1. Clear? It is equal to 1 means no dissociation, no association. Okay. So, what is I? The observed colligative property by normal colligative property or normal mass by observed molar mass. Two equations are there. And learn this. This is very important. I equal to 1? No. Association, dissociation. This was your doubt, right? Look here. I equal to 1. No association, no dissociation. I greater than 1 means what? Dissociation. I less than 1 means what? Association. So, the measuring molecular mass, the application is, we can use this for measuring the molecular mass of polymers by the osmotic pressure. That we already discussed in the previous one, the osmotic pressure we can use to calculate the mass of the polymers. Okay. So, we already discussed everything. In this chapter, we need to learn about the solution. It is a homogeneous mixture. What is the solution? Solution is a homogeneous mixture of solute and a solvent. And if it is made up of only two components, it will form binary solution. And there are a lot of solutions like solid solution, liquid solution and gaseous solution. And under that also we learned about the concentration terms, right? Concentration terms. Concentration terms we learned like molarity, mole fraction, mass percentage, volume percentage. Then we discussed about the ideal and non-ideal solution. What was ideal and non-ideal solution? Ideal solution means, and before that, after the concentration terms, we discussed about Henry's law. What is Henry's law? Henry's law, that means pressure is directly proportional to mole fraction, and we remove the proportionality constant like equal to kh into chi, where kh is the Henry's law constant. Okay. Then Raoult's law also we discussed. What was Raoult's law? Pressure is directly proportional equal to P0 chi. Pa equal to Pa0 chi A. Pb means Pb0 chi B. Okay. Isotonic solution means there won't be any difference. Both the solutions will be having the same pressure. So, there won't be any flow between the two liquids. That is meant by isotonic solution. Okay. So, ideal is there. Non-ideal solution is there. Ideal means which obeys the Raoult's law. Non-ideal means which does not obey the Raoult's law. And non-ideal is again classified into positive and negative. Positive means delta V and delta H mixing is positive. AB interactions will be weaker than AA and BB. AB interactions then opposite. Negative is also there. Okay, and draw the graphs, and it's very, very important for that topics. If it is asked for exam, you should draw the graph and explain with the examples. And after that, we discussed about the four colligative properties. Which are the colligative properties? Relative lowering of vapor pressure. One equation was the elevation and boiling point, depression and the freezing point, and the last one was osmotic pressure. And after the osmotic pressure, we learned about the abnormality in the colligative properties, and is calculated by the Van Hoff factor I. And what is the equation for the Van Hoff factor I? That is observed by the normal one. Like three equations we can use, and out of that, three calculations were given. If I is equal to 1, there won't be no dissociation or association. If it is greater than 1, what will happen? If it is greater than 1, dissociation will happen. Less than 1, association will happen. The normal molar mass divided by observed molar mass, normal colligative property by observed colligative property by normal colligative property. So, three equations are there which can be used to find out the abnormality in the colligative properties. Clear? So, these are the main topics in this chapter. Okay. So, we can end the live, we can end the session. So, if you are having any doubt, please do the comment so we can wind up the class. So, study well, and this is a very important chapter, the basic chapter, the first chapter of your class 12, and that is very, very important for your next next chapters also solution, like we know a lot of numericals are coming from the section. We can do another live related to the solutions numerical session. We can conduct it. Okay, so we can wind up the section. Bye bye. Thank you. Good night.